In the ODTBT program, resolving anomalies proves structural integrity. Addendum 22.9 targets two open questions. First, the framework uses mathematically incompatible formulas for lepton and meson sectors. Second, it requires an electron recursion depth of exactly 3. Any other integer causes failure. In conventional physics models, continuous curve fitting allows parameters to smoothly slide into place. Here, we are bound by rigid, integer-based constraints that refuse to be optimized. This creates a strict pass-fail condition for the entire architecture. The validity of these particle mass ratios depends on these rigid, unoptimized structural rules. If the specific depth of 3 and the split formula choices are arbitrary, the model is merely generating numerical artifacts. But if they are mathematically mandatory, the framework holds. We have to look at the physical composition of these particles to understand why the spinor channel topology diverges. Leptons, like the muon and tau, are elementary particles. Their recursive streams originate from one continuous point in phase space. To couple those streams, mathematics requires the RCAM-He v2 Pauli triplet, G1, G2, and G3. To handle streams from identical phase space, we introduce RCR indices, K1 and K2, to differentiate the interaction. Mesons operate under different topological rules. As composite particles made of distinct quark constituents, their points of origin are separated. This breaks the closure condition through flavor asymmetry. Because these two meson streams originate independently, they do not require interstream coupling equations. They only need a simple geometric mean of independent scalar locks to interact. The framework's codebase from Sprint 3 allows us to test this structural rule computationally. This chart shows the error margins when comparing these formulas. Applying the simplified meson formula to the elementary muon produces an error of 2,087%. When we apply the correct lepton formula, complete with the DHM and Huronian mean configurations, that error drops to 0.032%. The precise choice of spinor formula is a strict topological requirement, one that is entirely dictated by the particle's underlying physical composition. That confirms the formulas, but it leaves the second anomaly, why global consistency across all these particle masses anchors exclusively to an electron baseline depth of exactly 3. Every particle mass ratio in the ODTBT program is defined by a single fraction. It is calculated by dividing the particle's Lock potential by the electron's Lock potential. This introduces a strict physical boundary condition. The scalar Lock potential must remain less than or equal to 1. This mathematical ceiling becomes a severe constraint when calculating the mass ratios for heavy particles, like the proton at 1,836 electron masses or the tau at nearly 3,500. If the baseline electron denominator is too large, the only way the fraction could equal the mass of a proton is if the numerator exceeded 1, violating the laws of the framework. A mathematically minimized denominator is the only physical way the framework can accommodate high-mass particles without breaking its own boundary constraints. The exact mechanism that executes this required denominator suppression lives inside the mathematics of recursion depth 3. The foundation of the electron baseline is its phase strain, which the geometry defines exactly as the fraction 175/24. At a recursion depth of 3, the frequency modulation parameter evaluates to exactly 1.3. This isolates the sign term within the scalar Lock potential, determining the baseline's final magnitude. Multiplying the frequency modulation of 13/10 by the phase strain of 175/24 simplifies to the precise rational fraction of 455/48. This chart shows a standard sine wave. A wave hits absolute 0 at every multiple of pi, and 3 pi is roughly 9.4248. The fraction 455, a mathematical explanation, only holds weight if it aligns with empirical data across the known particle spectrum. To test this, we evaluate the complete published corpus of particle configurations exclusively at level 1. This means evaluating strictly discrete, integer-based depths with zero continuous curve fitting applied. This chart shows the level 1 error distribution. Locked identically to the depth 3 baseline, 9 of 10 particles simultaneously achieve sub% accuracy. 5 achieve excellent rates. The electron, muon, proton, and both kaons all fall below the 0.1% threshold. The remaining 4 resolved particles, the tau, the eta prime, and the charged pion, all comfortably clear the sub 1% threshold. The singular exception is the neutral pion, which remains excluded pending rigorous theoretical justification for its triple selection. Skepticism regarding these complex mathematical models often centers on the assumption that accuracy is just a byproduct of heavily optimized parameter tuning. The emergence of these sub-percent matches at discrete integer depths identifies them as fundamental bulk structural properties. In the framework's formal literature, the near coincidence of 455 over 480 mapping to 3 pi is formally categorized as mechanism E. Specifically, it operates as a denominator sector mechanism. It provides the exact structural suppression required to keep the baseline lock potential strictly anchored. Previous analyses identified similar Diophantine alignments in the numerator sector. Global consistency demands geometric tuning on both sides of the ratio. Continuous parameter optimization, what the model calls level 2, only refines these established boundaries. It does not create them. The equations program is governed by number theory and rational approximations of pi, operating independently of human parameter tuning. Addendum 22.9 officially resolves its 2 targeted anomalies. The dual formula architecture is computationally confirmed, and the depth 3 baseline is mathematically justified by mechanism E. But resolving those gaps exposes the next structural frontier. The underlying origin of the foundational phase strain, exactly 175 over 24, remains an unsolved mystery. Deriving the precise depth counting sequence directly from S12 bulk geometry is the primary objective for the next phase of research. The equations continue to reinforce a central premise. In this framework, the mathematical geometry precedes and determines the physical mass.